Sines, the birthplace of Vasco da Gama, the first European to reach India by sea, the discoverer of a route connecting the Atlantic and the Indian Oceans via the Cape of Good Hope. In this city, which is part of the history of sea exploration, a group of European researchers has laid the foundations for a totally innovative way of enriching our knowledge of the seabed through the use of autonomous robots. These waters were in fact the scenario where the tests of the WiMUST project took place. Funded by the European Commission within Horizon 2020 and coordinated by the Italian Inter-University Center on Integrated Systems for the Marine Environment, ISME, WiMUST has developed a system based on a heterogeneous team of cooperative autonomous marine robots for geotechnical surveying and geophysical exploration at sea. Traditionally, seismic acoustic surveys are made using a vessel that tows a powerful acoustic source and a group of streamers equipped with hydrophones. The acoustic source generates a sound that penetrates the seabed, and the return echo is captured by the hydrophones mounted on the streamers.
In order to be able to do that, we need to deploy huge resources. That means long cables being towed behind powerful vessels, and those cables can be up to 10 kilometers long, and sometimes we need to tow up to 20 cables. So this is a huge amount of effort to do this.
The idea proposed by WiMUST researchers is totally innovative, using underwater robots to tow the streamers and small autonomous vessels on the surface to house the acoustic sources, the sparkers.
Maybe people are not really aware, but the greatest risk that survey operations at sea has is the fact that you have a vessel towing all the equipment at the same time. If something breaks down, one component breaks down, everything stops. You cannot continue operations. You need to stop, repair, get the boat on land or whatever, but you cannot continue. And with the autonomous vehicles, it's as if all this risk is spread out through the vehicles. If you lose one vehicle, you just replace that vehicle. You don't stop operations, you just keep going. And that from an offshore work perspective, it's the enormous difference.
The researchers used two types of underwater robots, the Medusa from IST and the Folaga from Graaltech, optimized for the tasks required.
The first modification was to make the vehicle capable of towing the streamer, which is quite difficult to tow in the water because of the drag. So what we did was changing the thruster in order to have one with more force for towing the streamer. The second more relevant modification we did was realizing a module inserted in the middle of the vehicle and containing the different equipment needed by this application. In particular, we had inside the module the streaming, which is entering and is connected to its acquisition board.
On the Medusa, the special equipment for the mission is instead housed in the lower hull of the robot. Two different autonomous catamarans are used as surface vehicles, Delfilm from IST and Ulisse from ISME. Catamarans and underwater robots communicate with each other to cooperatively navigate and collect acoustic data for the survey.
The thing becomes relatively more complicated when some of the vehicles are underwater, because then you need to communicate with them and you don't have Wi-Fi or radio. So this means this has to be done with acoustic waves. So the vehicles that are underwater must receive the position from the vehicles on top via acoustic waves.
The catamarans are equipped with the Sparker from Geomarine Survey Systems and acoustic modems made by Evologics to communicate with the underwater vehicles.
Actually, we have two kinds of modems at different frequencies to allow for a duplex communication between what is on the surface, so the catamaran and AUVs. And in particular, we exploit the surface vehicle, so the catamaran, with the GPS to provide the vehicles with position information so that they can understand where they are, because the underwater vehicle cannot, of course, use GPS. And the high frequency modem is used to receive information from the vehicle and to implement seismic quality control. So we have some way to know if the survey is being done at certain level of quality and so on.
Knowing precisely the position of the vehicles moment by moment is of fundamental importance for the correct mapping of the seabed. Moreover, it is essential to have a very accurate synchronization of all the equipment used in the mission.
Challenge was solved using the integration of modems with atomic clocks, providing us the better possibility for the positioning just by transmitting the signals from the surface and receiving them at the same time in a synchronized manner on all the vehicles.
Another important element of the WiMUST systems are the streamers, towed by underwater vehicles, which host the hydrophones that receive the sound echoes reflected from the seabed. They have been specifically designed for the project because they must be light enough to be towed by the AUVs.
These streamers we use here are quite a bit shorter. Normally we go for streamers ranging from 50 meters to 150 meters. These streamers are, from the top of my head, I think 16 meters. So they're smaller, have somewhat less channels, but the number of streamers is higher than normal. We use 8 streamers in the WiMUST project.
The streamer behaves like a giant antenna receiving sound echoes. The flexibility offered by the robots have allowed WiMUST researchers to experiment different geometries of streamers.
The objective is to study the formation of the vehicles and optimize the position of the vehicles for estimating the bottom properties and obtain a better result than what would have been obtained without this optimization.
Software integration was one of the most complex activities in the project. Custom console modules and data acquisition modules were designed and coded together with cooperative motion control, navigation, acoustic and Wi-Fi communication. To guarantee the safety of the vehicles during the mission, the researchers have also designed and coded a specific motion planner.
In motion planning, the vehicles have to be brought from a certain configuration to a goal configuration, guaranteeing the avoidance of the collisions. In the context of WiMUST, this can simplify the logistics in terms of inter-vehicle collision avoidance and streamers unentanglement.
After 3 years of work, it is now the time to test the whole system in open water. 7 autonomous vehicles are deployed in the sea, 2 autonomous catamarans carrying the Sparker's seismic sources, 1 robot on the surface, and 4 towing streamers at a depth between 2 and 8 meters below the sea surface. The vehicles perform about 7 laps of a racetrack path, scanning an area of about 100 meters by 200 meters. The acquisition is a complete success. After the computer elaboration, the image of the seabed appears. It is the proof that the WiMUST system can be used to collect seismic data autonomously.
To the best of my knowledge, it's the first time that a similar setup is used to acquire the seismic data, and we are extremely satisfied on the results that we achieved.
In the future, it will be possible to use the system designed by WiMUST researchers in many fields, such as rescue missions, oil and gas exploitation, underwater construction, equipment installation, and underwater archaeology research. A new tool is now available for the exploration of sea depths.